So hello everyone, today we will discuss about x8, x16 and x32 in DRAM. So this we can see this is our typical DRAM, okay, and inside our DRAM we have these chips, okay, these black chips. And the thing to note over here is that our DRAM channel is of 64-bit wide and having a 8-bit of ECC code. So this ECC actually helps if there is any error in the 64-bit data that is supplied by the DRAM, then using this ECC code it can be corrected. Now let's come to the x8, x16 and x32 part. Now x8 actually means that from each of the chip I am able to get 8 bits of data. Okay, from each chip I am able to get 8 bits of data. So let's say my channel is of 64-bit wide, right? Now from each of the chip I will be getting 8 bits, 8 bits, 8 bits and 8 bits. So let's say in this particular picture there are 8 such chips, so which means that 8 cross 8 is equals to 64-bit. So we will require 8 such chips if the chip is of x8 width to get 64-bit data. Now let's say this particular chip is of x16. What will happen? In x16, since each of the chip is transferring me 16 bits of data, right, I will require only 4 such chips to form a 64-bit data. Fine. Since my number of chips required to transfer 64-bit data is getting reduced, my form factor can also be reduced. Okay, now I can have a much smaller RAM compared to the normal in x8 width DRAM chip. Okay, so over here I can see I can use this form factor. You can use this compact form factor in my laptops. Okay, so in laptops we usually have x16 chip width of in the DRAM. Okay, now let's talk about the benefits and demerits which comes with x8 and x16 and increasing width size. Now as the width size is increasing, okay, as the width size is increasing, the number of banks decreases. Okay, as the width size is increasing, my number of banks inside each chips are decreasing. Now what are banks? Inside each of my DRAM chip I am having small banks. Okay, so let's say these are my banks. This is bank 0, this is bank 1, this is bank 2, this is bank 3 and so on. And these are repeated in each of the chips. So this is bank 0, this is bank 1, this is bank 2 and like this in all of my chips banks are present. Now what role does banks play? Inside, let's say this is my bank 0 and inside each bank I am having rows and columns. And these rows and columns are what actually stores the data. Fine. And let's say I want to transfer an address, I want to transfer data which you, let's say, and on address 123. Okay, now I will break down this address into rows and columns. I will break down this address into rows and columns. Let's say my row number was second and my column number was third. So what will happen over here is inside this bank I will activate this particular row. Okay, I will activate this particular row and then I will activate this particular, the column was third, so I will activate the third column. Okay, I activated the third column. Now this time, so let's say when I am activating the row is called as TRCD and this is called TCAS, column axis strobe and row to column delay, I guess so. Okay, now when I activate, so this happens first and then when this particular operation is completed, let's say it completed in, let's say, 50 cycles, then this particular operation happens. Okay, after completion of this particular TRCD. Okay, now this will transfer me some amount of data. Let's say 8 bits of data got transferred from this particular chip. Okay, this transferred me 8 bits of data. Now how will I perform, how, but the width was 64-bit, right? So how will I be getting 64-bit data? So this was bank 0 in my chip, in my black, in my very first chip, in, let's say, in this chip. Okay, now the same will be happening, in all of these chips, right? So in bank 0 I will be getting 8 bits, in chip 1, in chip 0, in chip 2 I will also be getting 8 bits of data, and in chip 7 I will also be getting 8 bit of data. So together they will form a 64-bit data and I will use them. I will use it to send it to the CPU. Fine. Now the thing to note over here is there are multiple banks inside my chip, right? There are multiple banks inside my chip. Now, how will these banks play in improving the performance? Okay, how does these banks, what role does these bank play to improve the performance? The role is simple. Okay, let's say this is my chip 0 and I'm having multiple banks. This is my chip 1, oh sorry, this is my bank 1, this is my bank 2, and so on. Let's say when the data has been transferred from this particular chip, now I am pre-charging it. What does pre-charge means? Pre-charge means that when I have read this data, okay, when I have read this data from this particular bank, the data inside this particular cell gets lost and it is stored in some other device. So pre-charge basically means that whatever data that you have wrote, what you have read, to write it back inside this particular cell, okay, so that this particular data does not gets lost when it is later recovered from by or later referenced by the CPU. So while this particular data is being pre-charged, okay, my DRAM is sitting idle. So what my DRAM controller will do, so the DRAM controller sits inside the CPU, okay. Now my DRAM controller will tell that until this by the time this particular row is pre-charged, what you do is you try activating this particular row inside the bank 1. So what this will happen, what this will do is ultimately it will overlap time. Fine, it will ultimately overlap time. Now by overlapping time, we reduce the average waiting time. Okay, we reduce the average waiting time for a request to be served from the DRAM. So this actually helps in reducing overall average waiting time, and our latency actually gets reduced and my throughput becomes more. Okay, because more requests are getting served in the same amount of time, my throughput is getting improved, right? And let's say there are more number of banks, which will ultimately mean that there can be more throughput. Fine. But one thing to be noted over here is that when the data is being transferred from the channel, okay, no other bank can also send the data because the data bus is occupied by this particular bank. Fine. Okay, so this is this. Now let's, but there is one issue, right? So if let's say the increasing number of banks can give me more performance, so why not keep on increasing the number of banks? Let's make it 16 banks, 32 banks, 64 banks. Let's keep on increasing, but there is a catch to it. We cannot increase it beyond a certain limit. The limit is that each bank have their own row buffers in which the data read is stored. Okay, now this row buffer, or let's say call it as sense amplifiers, row buffer or sense amplifier, store the data which is read from this particular row and column. Okay, stores this particular data. Now these are very large in sizes electrically. Okay, so these are electrical components and they occupy a lot of space. So we cannot have more number of banks, as this particular area, this particular row buffer or sense amplifier will consume a lot of space and my storage density will decrease. Okay, my storage density will decrease inside a particular chip. So this is to be kept in mind, and an optimal number of banks has to be ensured so that it will be not too much, not much less. Okay, so this is the concept of having more number of banks. But since in x16 the number of banks actually gets reduced, due to which my overlapping thing kinds of gets reduced and my throughput kinds of decreases. Okay, so this is why x8 is preferred over x16 to get more and more performance. But there is one, okay, we will talk the other advantages in other videos. So thank you. If you like the video, then hit like and subscribe.